Okay, now I'm gonna walk you through how we calculate the electric potential energy in a capacitor. Okay, the procedure to calculate that is rather similar to the procedure of calculating the potential, gravitational potential energy of this object that you see right in here. Every time that I raise it against the force of gravity, I add gravitational potential energy to this device. My hand does some amount of work, and this amount of work is transferred to the object as potential energy. That's how we do it. And we do the same with the capacitor. It just happens that we don't raise the capacitor, right, against the force of gravity. We do something else. It's not obvious. That's why I'm going to walk you through. So here is a generic capacitor, two pieces of metal. This is an uncharged capacitor. No potential energy whatsoever applied to it. Because the capacitor is uncharged, its electric charge is zero. And because the electric charge is zero, the electric potential difference between them is going to be zero as well. Okay, so at this moment, there is no potential energy whatsoever. I'm going to I'm going to simplify this notation. Instead of writing that as electric potential energy, electric potential difference, I'm going to just simplify this notation and put the potential difference, electric potential equal to zero. Every time that I talk about electric potential, I am implicitly stating that's an electric potential difference. Okay, so here we go. And how we are going to add potential energy to this system of two capacitors. Okay, well, note that both pieces of metal here, they are made up not only of negative charges but positive charges as well, right? So hey, if at this point here I have negative charges, elsewhere those negative charges, the negative charges must be cancelled by a same amount of positive charges elsewhere. Okay? So if I have, let's say, 6 negative charges at this spot, we must have 6 positive charges at this spot. In order to build up electric potential difference, what do I have to, in order to build up electric energy, electric potential energy within the system, what do I have to do? I have to somehow get those negative charges that I have highlighted here and move towards the other capacitor. Okay? So here you go. I go ahead and just think that I have my hand here and I shove my hand into this capacitor, into this metal, and somehow I managed to pick up a bunch of negative electric charges, move to the other device. Okay? Because I took away some negative electric charges, the positive charges that I left behind start to attract the negative charges, right? And it's going to be sort of difficult to move to the other metal that makes part of my capacitor. By doing work against the electric force, I start to pump electric potential energy. Okay, so this process of shoving my hand into that piece of metal, get some negative charge, and move to the other piece of metal, adds potential energy in the same way that I add gravitational potential energy by raising this mass against the force of gravity. Okay? That's the analogy that you have between electric potential and gravitational potential. Okay, so here you go. Here are the electric force preventing you from moving those negative charges. And here is the force that your hand makes in those bunch of electric charges. Okay, the fact that I'm doing work to move this charge is adding electric potential energy. And eventually, after some effort, I managed to shove those negative charges into the other piece of metal. And what I did here, I just transferred, an infinitesimal amount of electric charge. Now I have a positive metal that's positively charged and another metal that's negatively charged. Because now there is a electric charge in both of those devices, in both of those metals, now we end up having not just a force, electrostatic force. Not only going to end up having an electrostatic force, but we are going to have also an electric potential difference between them. Initially it was zero, right? Just remember that initially it was zero. And now we have this electric potential difference between them that generates a electric potential energy in this system. Okay, so how do we get an equation that allows you to calculate the potential energy? Okay, so that's not that difficult. Okay, once you know the qualitative process to calculating that, to find that out, now we can start looking at the details of the derivation, of the mathematical derivation. Just remember that the work done by the electric field is the difference in potential energy, which, by the way, is Q times delta V, right? Strictly is Q by delta V. That's the very definition of electric potential, right? Is the electric potential energy divided by Q. To simplify the whole notation, I'm just going to write U equal to QV. But remember, I am extracting an infinitesimal amount of charge just like I did. And the infinitesimal amount of electric potential energy will become a V, which, by the way, is a function of Q times that infinitesimal electric charge dQ. Make sense, right? The V is going to be a function of the electric charge, right? If I want to find out what, and by the way, as we keep on removing the electric charges from one device to the other, the V is going to change as well. So in the next step, what do you do? We are going to integrate this equation. Now we integrated from an initial uncharged capacitor to a charged capacitor with charge Q. Okay? And how do we do that? Just apply the integral sign here. Okay. Everything is going to be inside this integrand, the VDQ. The charge is going to go from 0 to a big charge Q, which is going to be the final charge in your capacitor. At this point in time, we go back to the definition of capacitance. That's why it's so important for you to, and I'm going to just redefine as a Q here, right? Instead of big Q, let's define as a small q to stay consistent with the definition. Don't forget that this V here downstairs is a function of the charge. And using this definition of capacitance, we can write our electric potential in terms of the electric charge in the capacitor and a parameter that is constant for the capacitor. Depends on the geometrical configuration of the device. And now it becomes easier for us to here write this electric potential of my charge. Remember, the C doesn't depend on the charge, depends only on the geometrical parameters of the capacitor, and that applies to every capacitor. And now we have this simple integral that we can use to solve our problem. Okay? It's going to become Q squared over 2. Make it look nicer. I'll put the capacitance here. I'm going to rewrite it in a slightly different way. You know, I will rewrite it in the same way that we would write, let's say, that quantity that you know, right? And instead of putting the C downstairs, I'm going to put the C upstairs with a minus 1 power. Okay? Something like that. Why am I doing that? Because it's a more, this form that you see here is very much similar to that of the kinetic energy, right? Half of m v squared. So if you forget how the potential energy of a capacitor looks like, just remember the equation for the kinetic energy, where we still have a half here. We have a parameter that documents the inertia of this device, of a capacitor, and the charge squared. There is another way of writing this equation that's going to lead to an even easier format of this equation. Okay? Now that my capacitor has finally reached the, let's say, the full charge, right? You know, V over big Q now, right? Now we have V over big Q, which is big Q over C. Let's write that in different formats, in different forms, and see how it looks like. I'm gonna, in the first step, I'm going to eliminate the electric charge from this equation here. I'm going to eliminate this functional dependency to simplify my equation. Okay, and my electric potential now, my electric potential energy now becomes what? See, something like that, right? And let's see what else we get. We can distribute the squares and look what we end up getting. Another equation that's even more familiar compared to the kinetic energy, right? Now the C is upstairs with this new format of the equation. And the big V, which is electric potential, is squared as well. One more. Let's look at one more way of representing it. Okay. Another way of representing this equation is by eliminating the C. C is Q over V, right? And when you do that, you place it right here. Okay, and we end up getting half of QV. So three different equations for the potential energy of any capacitor. Notice that everything that we did here was for a generic capacitor, because every capacitor obeys this relation here that you see. Okay. So here you go, one relation. Now I'm going to put that 1 over C, right? 1 over C. We don't need this C2 minus 1 anymore. We have this other relation here. And we have this final relation here. 1, 2, 3. Let's do an example. Let's do a numerical example. A numerical example. Example using real life capacitors. Okay. I want to refer you to that site that I showed to you in Wikipedia before. Notice that we have all those bunch of capacitors here. See, this capacitor here has a capacitance of 100 microfarad with a maximum voltage, by the way, of 16 volts. This one here has a larger capacitance, 4700 microfarad, with a maximum voltage that can hold the charges, otherwise the capacitor start to ionize the dielectric around it, at 35 volts and so on. Let us calculate the maximum potential energy that this blue capacitor, this large blue capacitor, can store. Okay. Let a capacitor of 4700 microfarad, 4700 microfarad, and a maximum electric potential of, going back there, 35 volts. Of 35 volts. Determine the maximum amount of energy that this capacitor can store. Okay? Solution. All that thing involves is just numeric calculation, nothing more. We're given only the capacitance and the electric potential. We are not giving the amount of charge. The amount of charge is rather difficult to measure. So we stick to the value of electric potential. We use this equation here. Going back to this software of mine, here you go. So half C P squared. Okay, C is 4700 4700 microfarad. and the voltage is 35 volts. Don't forget this value that we are talking about is just the maximum energy that that a specific capacitor can carry. Substitute all the values here. Stick here the capacitance and expand. I'm gonna calculate that, compute that, calculate. That's what I'm getting here. Well, we didn't finish. Let's make sure, you know, that Faraday, right? Faraday is what? The unit of Faraday is what? Is unit of charge divided by the unit of voltage. Okay. This volts is also voltage, and look, don't forget the V. The V is what? V is joules divided by Coulomb. We substitute it here. Easily fine. And that's the type of potential energy that I get from that small device, 2.8788 joules. Okay? 2.8788 joules. Compare this much energy to that of a 1 kilogram block raised 1 meter, right, above the ground. Here's the electric, the other one is going to be the gravitational potential energy. So I'm going to lowercase g. It's going to be what? mgh. Well, m here is going to be 10 times 1 is going to be 10 joules. Okay? So a 1 kilogram block is going to store, when we raise 1 kilogram block a meter high, we're going to store 10 joules of energy, of potential energy. And this one here is a smaller device, by the way. It's smaller than your 1 kilogram block that you can carry all along anywhere, right? Have you ever thought about keep on carrying this much of energy around the streets? You know, you go ahead, raise your mass 1 meter high. You don't want to lose this gravitational potential energy, and then you want to take this gravitational potential energy somewhere else, right, to another place, and then you go walk around the streets with this block raised with your hand. Eventually, you're going to get tired, right? If you want to do the same with a capacitor, all you can do is buy 3 of those capacitors, put in your pocket, carry along, and you have 4 capacitors, right? A little bit less than 4 capacitors, a little bit more than 3 capacitors. Put in your pocket, walk around. It's not going to weigh 1 kilogram. So that's what we have. What we're going to do next, we're going to calculate the electric potential energy of a parallel plate capacitor. Okay? So here again, this equation is good for any capacitor whatsoever. Doesn't matter what's the geometrical configuration. This equation applies to a cylindrical capacitor, applies to a parallel plate capacitor, applies to a spherical capacitor, and any other arbitrary geometry. We want to know what's going to be the equation in terms of geometrical parameters of this parallel plate capacitor, right? So how do we do that? We start with the capacitance of a parallel plate capacitor. Okay. And I'm going to use this equation right in here. Okay. I meant we're going to use this equation right in here. And just remember that the capacitance of the parallel plate capacitor is the area divided by the distance between the plates, right? So I'm going to substitute this C right in here in this parameter, okay, in this equation, and that's what we get. Furthermore, I'm going to remind you that there is a relationship between the electric potential and the electric field. Remember that? The electric potential between the two plates is going to be the electric field times L. And that's what I put it here. That's what I got here. This L is going to be squared, and we'll be able to cancel out this other one downstairs. Okay? And the electric field will remain squared. And look what we get. This is the area of the capacitor, and this is the length of the capacitor. Those two parameters combined become the volume of the capacitor. And that's what we end up getting for the parallel plate capacitor. I'm going to put that right here. Half epsilon naught volume of the capacitor times the electric field squared. But now I'm going to do something else. I'm going to pass this volume to the other side. And what you're going to get is going to be that the electric potential energy density of the device. Okay? And what do we end up getting? We end up getting this simple result here, half epsilon naught E squared. Okay? So that's the potential energy density of our capacitor. Important to state that even though we derived this equation for a parallel plate capacitor, this result is good for any capacitor geometry. Okay. We can derive for the other ones too, but I just want you to be aware that this. But remember, it's just the energy density, just the energy density that's applied to all capacitor geometry that are available out there. All this calculation that we did was just for a vacuum between the plates of the capacitor. So those equations that you saw that we derived applies only to the case where there is only vacuum or air between the plates of the capacitor. Okay? So here you go. It's a capacitor that has vacuum between these plates. So the question is, what if instead of vacuum we start to introduce some dielectric material in there? Every time, keep that in mind, every time that you have capacitors, you must have a dielectric material introduced between the conductors of the capacitor. Otherwise, the capacitor itself will become discharged. It must be a dielectric material to hold the charge of the material. And this dielectric material can be air, can be vacuum, okay? All those calculations that we did was for a dielectric of vacuum or and air as well, because they have almost the same dielectric constant. So what happens? That you introduce a different dielectric material. What happens if you introduce glass between the plates of the capacitor? What happens if you introduce plastic between the plates of the capacitor? That's what we are going to do right now. That's what we are going to derive right now. Okay? The way it goes is like that. Here, vacuum between the plates of a capacitor, right? We're doing here the parallel plate capacitor case. And we do have this electric field between those two plates, those two charged plates. And then if I decide to introduce a piece of cardboard or a piece of glass or a piece of plastic, something is going to give him here. The electric field still goes through those devices, okay? The electric field does permeate the material. Yes, it does. But something else happens inside this material, okay? In addition to the electric field that is inside the material, what happens? This electric field, it polarizes the molecules in the material, in the dielectric material. So without the electric field, there is no polarization. No? And those molecules becomes like a electric dipole. Okay? Without this material, without this electric field, there is no polarization of the molecule, and the molecule just like has no electric field of itself. Okay, that's what it happens. So here we're gonna go see that what happened here. We have this external electric field, and because of the polarization of the molecules inside the dielectric, a electric field within the molecule itself is created. That's what those black arrows are all about. And it cancels out a little bit of the external electric field. So the net electric field is going to be a little bit weaker than what we originally had without the dielectric material. Okay? So here you go. Here's the net electric field, right? Side by side, this is the electric field, and then when we put the dielectric material, the electric field decreases by view of the polarization of the molecules of the dielectric material. That's why the lines, the arrows are a little bit more widely spaced. That's what you must have in mind. Once you recognize that, once you realize that, we can start to build up a theory that explains what happens inside a capacitor with a dielectric material. Okay, I already told you that the electric field becomes weaker. Consequently, we can write that the electric field, the new electric field, is going to be the electric field with vacuum divided by a number that's greater than 1. That's a kappa. We call that a kappa. The electric field inside of capacitor with vacuum there inside, no substance, but just vacuum, is given by this value here. But if you introduce a dielectric material, this field here becomes weaker. And this ratio, this factor that you see downstairs here, is exactly what we call the dielectric constant of different materials. Okay? And there are tables that documents this value here for kappa. If we are talking about air or vacuum, this kappa is equal to 1. Okay? For air and vacuum, this constant is equal to 1. For other materials, the constant is different, is greater than 1. So we can consult the internet to find out what values that would be. Here is one of those tables. Let me go back here. Here is one of those tables. I cannot zoom in more than that. But you can see air, dry air is the electric constant. is 1 bakelite, 4.9 mylar. You might know mylar, right? It's 3.2. Nylon is 3.4, and so on. Strontium titanate, 233. Glass, 5.6. Water, 80. Water has this dielectric constant of 80. It decreases drastically the value of the electric field. Polystyrene, polypropylene, paraffin, paper. Paper is a dielectric material, 3.7, and so on. Okay, those things are documented out there. And now that we know how the electric field behaves inside a capacitor with a dielectric material, we can find out what is the effect of this dielectric material in the electric potential. Okay? Just remember, just remember that the electric potential between the plates of the capacitor is going to be the electric field times the distance between them. But the new electric field is the electric field in the vacuum divided by the constant kappa. Okay? And by the way, E naught times L is the electric potential between those two plates whenever you have only air or vacuum. So you can see that the new electric potential with the dielectric material also decreases by a factor of kappa. So in other words, the system loses energy when we insert a dielectric in between the plates. What about the capacitance? Okay, when you have a capacitance, we have here the capacitance of the material, right, of the capacitor is Q divided by V naught. Q doesn't change. Okay, what changes is the electric potential in between. If I put 1 millicoulombs in the plate, in between the two, in each of the plates, minus 1 millicoulombs plus 1 millicoulombs in the other plate, the amount of charge will remain the same whether you put a dielectric material there or not. Okay, what's going to change is going to be the electric potential. So that's what we have here for the capacitance with air or vacuum in between the plates. What about the new capacitance? The new capacitance is going to be Q over V. The new V is going to be V naught over kappa. And we find out that the new capacitance increases. Okay, Q over V naught is the capacitance with the air or vacuum in between the plates. Here you go. Kappa, remember, is greater than 1. Okay, what about the energy? What about the stored energy? We just go ahead and get the stored energy that we derived before, half C naught V naught square, right? We are going to here write the electric potential for our capacitor with a dielectric in between, CV squared. C is going to be kappa C naught, and V is going to be V naught over kappa. Because this term is squared, the final energy stored is going to be less by a factor of kappa, right? You square this term here, you get V naught squared over kappa squared. Kappa squared cancel out with kappa, and we have a factor, a decrease in the energy by a factor of kappa. Okay? So electric potential energy decreases as well. And the last chapter here in the book is about dielectrics and Gauss's law. Okay, Gauss's law is changed slightly because of the fact that we have a dielectric there in between the plates. Okay, I'm not going to ask that in the exam, but it's a good thing that you know, so you can understand how you derive problems, right? What's going to happen here? The new thing about the dielectrics is that if you do not have any air, if you have air or vacuum here inside, you don't have any charges here within this Gaussian surface. When you introduce a dielectric, then you are going to have those additional negative charges that are polarized in the dielectric, and that changes slightly the amount of charge, the charge that's enclosed, right? And here is the electric field, right? Now that we have less of a charge, the electric field is going to be less intense as well. And there is a relationship between Q minus Q prime in terms of kappa. And we do know that E is equal to E naught over kappa, right? And this kappa factor, that goes here introduces a value for the charge that's less, because this number here is greater than 1. Here you go, that's what you get. That's a relationship that you get between Q minus Q prime and Q over kappa. So if you know kappa, you may derive the value of Q prime. If you know kappa and the amount of charge in your capacitor without the dielectric, you can find out how much charge is going to be induced there in the surface of the dielectric. Okay, so that's what we have for this chapter. You don't have to worry much about this last section, but it's good that you know, but I'm not gonna ask that in the exam, okay? So I see you again some other time, and I'll be posting this recording soon. Thank you and bye bye.